So just as in the last video, we considered the notion of complex limits, today we would like to extrapolate continuity into complex analysis and discuss how that works for complex functions in abstraction mostly, or for complex numbers in abstraction as well. So today will really involve going through a number of theorems that we have and sort of finishing up our little discussion of complex functions, complex limits, and complex continuity. Everything that you would sort of see in a first unit real calculus class for Calc 1, say. And we've done things in abstraction just because we don't really need to do things otherwise, because they're fairly simple and we should know what they mean already. We know how to do epsilon delta proofs, we know how to find limits already, so it's really not a lot to ask to just extrapolate this to consider imaginary numbers as well. Of course, things will get a little bit more nuanced later on, but for now, it's looking pretty simple. Let's get started anyways. So there are three definitions and theorems I'd like to discuss before considering actual examples or actual profound realizations that we have from some of these continuity postulates. Let's get started with the definition. We will let f be a function defined in the neighborhood of z0. So this is something that we did in the past. We considered some function in the complex plane, or some space in the complex plane. We considered some z0, and we considered then some little neighborhood. We call this little neighborhood a little circle in the complex plane, perhaps with a radius of epsilon. So we have this little radius, and now we would like to consider what continuity means. So if f is defined in the neighborhood of z0, then f is said to be continuous at z0 if the limit as z approaches z0 of f of z is equal to z0. Bad notation, I should have put the function in here, but that's okay. We'll leave it there for now. Anyways, so that is our definition for continuity, which should make sense. This is essentially saying in the real calculus, when you say a function is continuous, if I zero in on this point here, as I go in around a little open interval, they keep going in, I actually approach this level. I don't approach some other level that you might have in, say, a removable discontinuity. So that's what continuous means. It's very similar to the notion of continuity in the real calculus, but of course we're dealing with complex functions. Second of all, this is a theorem, but it is a little bit more complicated than this. Of course, there are lines of sort of all of the properties that you have, but I'm not going to write them out because they're, of course, the exact same as the properties that you have in Calculus 1. So it is a theorem that we say that all of the limit laws of real functions will carry over to complex functions. So what do I mean by this? Well, I'm saying that, say, the limit as z approaches z0 of some function f of z plus g of z is equal to the limit for f of z plus the limit for g of z. So this obviously carries over to subtraction, exponentiation, and multiplication, and division, whatever have you. So in theory, it should all work. So you don't really need to think about it all that much. You can take the limits as you normally would, just considering that you might have a complex number in there. Of course, a little bit easier to do this practically than analytically, as we were doing with the epsilon delta proof, can just plug in numbers for this and solve as if we were solving a real limit. And then finally, a theorem here is that similar with the limit laws, the continuity properties also hold. So if f and g are continuous at z0, then so is f plus g, f times g, and f over g, given that the quotient is not 0, right? Of course, if you're dividing by 0, then that's a problem. That's been a problem always, will always continue to be one. And then just to note that we can extrapolate from these two theorems, since we are allowed to multiply limits, since we're allowed to add limits and all of that jazz, we can prove easily that the constant functions are continuous on the complex plane, and also that the constant linear function, f of z equals z, is also continuous in the complex plane. So given these two facts, right, to build polynomials, we need to multiply constants by powers of z, and because we have those continuity laws and those limit laws, we're allowed to do that, and it still holds. So if, say, z is continuous at z0, and z, another function z is also continuous at z0, we can multiply the two together, and then at z times z, or z squared, is also continuous at z0. So from this, you can build the polynomials, and you can also build the rational functions. And from this, we see that they're continuous on their domains, and this should be a reasonable step that we're making here. And then finally, we can finish off with a little bit of an example, considering Staff and Snyder's example 1.2.3. This is a three-parter, quite the doozy, but not really, because it's just plugging in some numbers. We would like to find the limits as z approaches 2I of the following functions, such that f sub 1 is equal to z squared minus 2z plus 1, f sub 2 is equal to z plus 2I over z, and f sub 3 is equal to z squared plus 4 over z times z minus 2I. All right, so we'll get cranking on these. For the first solution, we are going to consider limit as z approaches 2I of f sub 1. We're just going to plug in 2I, so we're going to get 2I squared minus 2 times 2I. We can just plus 1, and we can multiply this out. We can do all of the algebra that we need to. We get 3 minus 4I. Fairly simple. For B, we have limit as z approaches 2I of f sub 2, which of course we're again going to plug in 2I, which is going to be equal to 2I plus 2I over 2I. Cancel out some i's. 2 plus 2 over 2 is equal to 4 over 2 is equal to 2. There we go. And finally, for C, a little bit more nuance here. You've got to remember that trick that you get sometimes, but z squared plus 4 turns out can be factored into z plus 2I times z minus 2I. That's one of the other things you need to remember when dealing with complex numbers. They can be factored even when you have the plus instead of the minus. The difference of squares is not exclusive anymore. You can have a sum of squares as well. So if z minus 2I times z plus 2I over z times z minus 2I. That should be a z, not a 2. And this is equal to z plus 2I over z. And that's because we've canceled out the factors here. If I were a little bit better with the animations here, I would have put a z there, but a 2 looks so similar to a z. We cancel that out, and then we get z plus 2I over z, which gives us, once again, the limit that we had there, because that was our f sub 2. So we can skip all of that algebra and go straight to 2. So that's the notion of continuity. That's the notion of sort of limits evaluation. That is not a part of the epsilon delta proof, but that's sort of how we deal with the limits in the complex plane. In the next video, we want to consider more the idea of the complex derivative. It's going to give rise to a series of functions that we endow the property of being analytic with. So we'll get into the actual notion of an analytic function and the notion of a complex derivative, all very exciting stuff. So we'll talk more about that in the next video, and we'll see you then.